Okay, so what I am going to now do is to tell you about another important property that comes because of the Noetherianness. Okay, so what I just explained in the previous lecture was that the Noetherianness of a topological space allows every non-empty closed subset to have a Noetherian decomposition, that is, it can be broken down into a finite union of irreducible closed subsets, non-empty irreducible closed subsets, and if you assume that this union is not redundant, that is, no subset in the union is contained in some other subset in the union, then this union this decomposition is unique, that is, the members of the union are unique. Okay, so and that is the reason why any algebraic set, any closed subset of affine space for the Zariski topology can be written as a finite union of affine varieties. So this is one of the reasons why we call affine varieties as building blocks of algebraic sets, and it is a general philosophy that affines are building blocks of algebraic of structures in algebraic geometry. And now I am going to give you another reason for the importance of Noetherianness. Okay, so that's got to do with dimension. Okay, so the aim is somehow to try to tell you the obvious thing that you will expect, that the dimension of affine n space is n. Okay, that's what I'll try to explain. But so what I want you to begin with, not get confused with, is the following. See, if you take affine space which is an, it's just as a set, it's just kn. Okay, it's n copies of k, where k is an algebraically closed field. Okay, and if you take kn as a vector space over k, then it's very clear that it is n dimensional, because it's a finite dimensional vector space, and n copies of k as of a field k will be dimension n as a vector space over that field. Okay, because for example, you can always write down the standard basis, okay, which consists of 1 in the ith place and zeros elsewhere, right. So but therefore if you think that I am trying to say that the dimension of kn over k as a vector space is n, then you are mistaken, because that is not what I am trying to say. I am trying to define dimension in a completely different way. I do not want to think of kn, especially an, affine n space, I do not want to think of it as a vector space. Okay, we are not here worried about the vector space properties. Okay, we are worried about the topological properties. So therefore what this calls for is how to define dimension of a topological space, how to define dimension of a topological space. So the answer to that is the dimension can be defined by taking the largest possible, namely the supremum of lengths of strictly decreasing chains of closed subsets. Okay, and in an analogy you can compare it to the vector space situation, okay. So you take any finite dimensional vector space over a field, there if you look at subspaces of the vector space, then if the vector space is of dimension n, then the largest strictly increasing or decreasing, whichever way you want to see it, chain of proper subspaces will be of length n plus 1, because it will start from 0. If it is increasing, it will start from the 0 subspace and it will end with the full vector space, and at each stage you will get a bigger subspace with dimension 1 more, okay. So you start with 0 and you end with n, so you will exactly get a chain of length n plus 1 of strictly increasing subspaces, and that is the maximum possible, okay. So in the same way the analogy is that for a topological space you can define the dimension to be the supremum of the lengths of a strictly increasing chain of irreducible closed subsets, okay. And this leads to a very good definition because it has got to do in the case of affine space, it has got to do with commutative algebra, namely with the polynomial ring. So in what way I will explain now. So let me make this definition. So what is it? So the aim is to so the aim of this lecture, at least the beginning, is to show that the Noetherian condition is very helpful to define and show that the dimension, topological dimension of affine n space is actually n, okay, and it will involve commutative algebra, as you will see. So here is my definition. For a topological space X, we define dimension of X, okay. So this is called the topological dimension, okay. Some people write dimension with a subscript TOP, okay, and sometimes we might just omit it, okay. So whenever I write dimension of a topological space, it's always topological dimension. What is it? This is defined as a supremum of all n, a set of all n, such that there exists a chain of irreducible closed subsets Z0 properly contained in Z1, properly contained in Z2, and so on up to Zn. So here is the the definition of what dimension of a topological space means, okay. So and mind you, I am starting with Z0, all right, and I assume that, just to check that I am on the right track, I need to also say that all of and perhaps I have to put the condition, I don't have to, okay. So Z0 is already non-empty, because see, I was just worrying whether I have to put the condition Z0 is non-empty, but then I am saying that they are all irreducible closed sets and therefore they are already non-empty, okay. But mind you, I am starting with 0. This is very, very important, starting with 0, okay. So now you see, so see, what I want you to understand is that this is let us examine this situation when X is affine space, okay. So take X equal to an k algebraically closed field, So you take K to be an algebraically closed field and look at affine n space over K, okay. Then you know that for the Zariski topology the closed sets here they correspond to the irreducible closed subsets here, they correspond to prime ideals in the polynomial ring in n variables, which is thought of as a ring of functions on the affine space. So what will this definition translate to here? It will translate to the following: dimension of an k is equal to the topological dimension is the supremum of all the n such that there exists a chain of prime ideals p naught. So let me use script p naught properly containing p1 I think I'll have to rather I have to number it the other way around. P0 P1 Pn, okay. So by this definition this is what you get, okay. You have a chain of prime ideals, okay, and it starts with p naught and goes up to Pn, and you take the supremum over all n. Now the fact is that so since you are looking at chains of prime ideals, strictly increasing chains of prime ideals, what this relates to in commutative algebra is called as height of a prime ideal, okay. So let me recall what that is, okay. So what is a commutative algebra involved? Let me explain that to you. So what we do is let R be a commutative ring with 1, okay. Let P in R be a prime ideal, let this be a prime ideal. Then what you do is then we define height of P, okay, height of P written as HTP to be the supremum of all the n's such that there exists a chain of prime ideals P naught properly containing P naught contained in P1 properly contained in and so on to Pn, okay. We define the height of a prime ideal like this, alright, and with of course with Pn equal to P, yeah, right. So in other words, you look at a chain of prime ideals which ends with P, and you look at the largest possible such chain. Of course it need not be finite at all, okay. You may always find a chain like this for every n, it might happen. So but if it doesn't happen like that, then you take the supremum and that will be a finite number and call that the height of the prime ideal, okay. And see, here comes the following fact. Suppose R equal to k of, so let me write this, f of x1 etc. up to xm modulo j where f is a field and J is a prime ideal. Suppose R is of this form. Your question is whether this is an ascending chain or whether this is a descending chain. Actually the truth is that if I put it either way, anyway I am going to get the same number, okay, whether I put it as if I start with Z0 and go up to Zn and it is an ascending chain, or if I start with Z0 and Zn and it's a descending chain, anyway it's that n that I am worried about, supremum of that n that I am worried about. So it really wouldn't matter if I put you know the inclusion this way or the other way, okay. But there is an issue when you come to the ring, and I will explain that now, okay. So you see we are assuming R to be of this form, that it is a polynomial ring over a field modulo a prime ideal, okay. That means that R is an integral domain. This implies that R is an integral domain, okay. Then so now what you can do is you can look at Q of R. This is the quotient field of R, or it's otherwise called as field of fractions. Of the integral domain R. This is just the field of fractions of the integral domain R, okay. Mind you, this is a ring and you are going modulo a prime ideal. A ring modulo a prime ideal is a domain, okay, and if you have an integral domain you can form the field of fractions just like you form rational numbers, the field of rational numbers from the ring of integers, which is an integral domain. So you take the field of fractions, and then what you can do is that you can look at you can see that this will contain f, okay. Clearly QR contains f, because you see f is anyway contained in the polynomial ring as constant polynomials, okay, and you are going modulo a prime ideal, okay. So in particular you are not going modulo everything, okay. So the fact is that you are certainly not, since this is a proper ideal, you are not certainly going modulo the elements of the field, okay. So the elements of the field still remain invertible in the field of fractions of R, okay. You can see this for example in commutative algebra either by looking at the universal property of a quotient field, or you can use the universal property of localization, okay. For Q of R is actually the localization of R at the 0 prime ideal, which means you invert everything outside 0, okay. You localize with respect to the multiplicative set which is the complement of 0, okay. So now the point is when you so in other words what you have now is you have an extension of this field, you have the field f and you have this field extension. Now once you have an extension of a field, in field theory you can talk about many things about the extension. First of all you can ask whether it's algebraic. If it's not algebraic you can check if it is transcendental, and if it is transcendental then you can define what is meant by transcendence degree, okay. So let me quickly recall, if you have a smaller field and you have a bigger field, then we say that the bigger field is algebraic over the smaller field if every element in the bigger field is obtained as a 0 of a polynomial coefficients in the smaller field, okay. And if there is an element which is not the 0 of an element of any polynomial in the smaller field, then that element is called a transcendental element. For example if you take real numbers over rational numbers, okay, then the number e which is used when in defining the exponential function, or the number pi which is used in trigonometry, okay, they are all transcendental, though of course the proofs of these facts are not so easy. E and pi are transcendental numbers, and they are transcendental numbers because you cannot find them as roots of an equation in one variable, polynomial equation in one variable with rational coefficients, which is the same as looking at with integer coefficients, okay, because you can always clear denominators. So the moral of the story is that you do have fields which have transcendental elements. So R, the field of real numbers, is transcendental as a field extension over the field of rational numbers. And once you have transcendental elements, what you can do is you can actually define, you know, what is called as a transcendental version of dimension, okay. So what you can do is you can mimic what you do for a vector space situation. See, in a vector space situation what you do is how do you define the dimension of vector space? The dimension of vector space is defined as the maximal number of linearly independent vectors, okay. So in other words what you do is you take a maximal subset of vectors which are linearly independent and take its cardinality and call that cardinality as the dimension of your vector space. So the dimension of the vector space is just the cardinality of a maximal set of linearly independent vectors, okay. Now you just mimic this in algebra, and what you do is instead of linear independence, which is used in the situation of vector spaces, you now use algebraic independence, which is the analog that you use in algebra in ring theory, okay. So what you do is if you have a bigger field containing a smaller field, okay, and suppose the bigger field has some elements which are transcendental over the smaller field, namely if it has elements which are not zeros of polynomials with coefficients of any polynomials with coefficients, polynomials in one variable with coefficients in the smaller field, then you can start looking at a collection of transcendental elements, okay, but put the condition that also put the condition that this collection of transcendental elements is algebraically independent, okay. So you know, a collection of elements, finitely many elements in a bigger field is said to be algebraically independent over the smaller field if these elements, okay, they do not satisfy a polynomial in as many variables with coefficients in the smaller field, okay. So please try to understand, when you do it for a vector space you will say that a bunch of vectors, finitely many vectors, are linearly independent if they do not satisfy a linear polynomial in as many variables with coefficients in the base field. Now what you are doing is, instead of requiring a linear polynomial in so many variables, okay, as many variables as the number of elements you are looking at, you are only saying that now you also assume that you cannot find a polynomial relation. You are only saying, so let me repeat that, if you have finitely many elements of a bigger field, we say the finitely many elements of the bigger field is they are algebraically independent if they cannot, if they are not, they do not have any polynomial relation between them with coefficients in the smaller field. In other words, they are not zero of a polynomial in as many variables with coefficients in the smaller field. Such a subset of elements is called an algebraically independent subset of elements, okay. Now what you do is, just like in the vector space situation, you took a maximal linearly independent set and took its cardinality and called it the dimension. You do the same thing here. What you do the analogous thing here. What you do is you take a maximal set of transcendental elements which are algebraically independent, okay. Take a maximal set of algebraically independent elements and take its cardinality and call that as the transcendence degree of the bigger field over the smaller field, okay. So the transcendence degree of the bigger field over the smaller field is the cardinality of the large maximal number is the cardinality of a maximal set of algebraically independent elements. Just like in the case of a vector space, the dimension of a vector space over the base field is the cardinality of a maximal linearly independent set of vectors. The same way the transcendence degree of a bigger field over a smaller field is the cardinality of a maximal algebraically independent subset of elements of the bigger field which are algebraically independent over the smaller field. Okay, that is called transcendence degree. It just mimics what we did for dimension in the linear case, okay, the vector space case. So the beautiful theorem is that if you calculate the transcendence degree of Q of R over F, that turns out to be what is the Krull dimension of R, okay, and the Krull dimension of R is supposed to be the supremum of the heights of its prime ideals. Okay, so let me write that. So here, so maybe okay. So let me do. So there are quite a few things that I have mentioned, but you can kind of try to at least understand them heuristically now and then do further reading. So define for any commutative ring R with 1 Krull dimension of R to be equal to the supremum of height of P where P in R is prime. Call this the Krull dimension, and the notation for that is dimension Krull R. Okay, then here is a theorem. So it is a theorem from commutative algebra and field theory which says the following: if R is equal to f of x1 etc. up to xm modulo j, where j is a prime ideal, then transcendence degree of quotient field of R over F is equal to the Krull dimension of R. So please understand this theorem. It's a very basic and of course a very important result. What it does is it tells you what the Krull dimension of an integral domain, which is a finitely generated algebra over a field, measures. It actually measures the number of algebraically independent elements in the fraction field of the integral domain over the base field. Okay, so this is a so you know in some sense this side is analogous to what you do in linear algebra. When you have a vector space over a field, then the dimension of the vector space over the field is the cardinality of a maximal linearly independent subset of vectors which are linearly independent over the base field. In the same way, when you have a field extension of a field, then the transcendence degree of the field extension over the smaller field is the cardinality of a maximal set of algebraically independent elements here over which are algebraically independent over the base field. Okay, and in the case of linear independence, the condition is that those elements those finitely many elements don't satisfy a linear polynomial in as many variables with coefficients in the base field, and in the case of algebraic independence the condition is that those finitely many elements do not satisfy a polynomial of higher degree in as many variables with coefficients in the base field. That is the analogy, okay, and that these two are equal is the theorem from commutative algebra, okay. And I need also another theorem, and I think this stating this theorem will in retrospect check whether I have muddled with the inclusions in this definition or in this definition, okay. So what is the theorem? So what this theorem says is that this theorem actually connects the height of the ideal with the dimension of the quotient, okay. So the theorem is with R as above, that is R is a polynomial ring in finitely many variables over a field modulo of prime ideal, okay. Height of J plus dimension, Krull dimension of R is equal to the Krull dimension of this. So what I want to basically say is that if you are looking at J equal to 0, okay, if you are looking at J equal to 0 and you look at height of the 0 prime ideal, then the height of the 0 prime ideal is just 0, okay, because I can start with 0 and I have to, and that's it, I cannot make it any larger. So the height of the 0 prime is just 0, okay, plus the Krull dimension of R will just give me again the Krull dimension of R, because R in this case if I put J equal to 0 then R is actually f of x1 etc up to xm, and the Krull dimension, so of course if I put J equal to 0 I will get I do not get anything, but the point is that the Krull dimension of this is actually m, because the Krull dimension of a ring is actually the transcendence degree of the quotient field of that ring over the quotient field of that integral domain over the base field. So if you take a polynomial ring in m variables and look at its quotient field, you will get the field of quotients in n variables, okay. So the quotient field of this will be f round bracket x1 through xm. This is the set of all quotients of polynomials in m variables, with of course the denominator being non-zero. And as you can easily see, you have to check that there are this if you take the quotient field of this, the number of linearly algebraically independent variables will be m, it will be these x1 through xm, okay. You cannot have more than m algebraically independent elements over f, okay. So what this will tell you is probably I do not need this now, maybe I will need it later when I look at the general case of an affine variety, but for the moment what you get immediately from all this is that the dimension of your affine space, okay, the dimension of your affine space will be by definition it will be the supremum of all these things, okay, and you can see that this is the same as the Krull dimension of the ring of polynomial functions on the affine space, which is equal to n, okay. So what I want you to understand, probably I do not need this now, so maybe I will do the following thing. For the moment let me let us not worry about this, okay, let us not worry about this, this is not immediately relevant for the discussion, but this is what is important. Put R equal to k x1 etc out to xn, we get dimension topological dimension of an is equal to dimension Krull of k x1 etc xn, which is by definition equal to, which is by this theorem equal to the transcendence degree over k of the quotient field of k x1 etc xn, and that is of course equal to transcendence degree over k of q of x1 etc xn. This is the notation for the quotient field of k round bracket x1 through xn is the quotient field of k square bracket x1 through xn, and k round bracket x1 through xn consists of ratios of polynomials from this ring, polynomials in these n variables, with of course the denominator polynomial being non-zero, okay, and this is equal to n. The transcendence degree of this is n, okay. That's again a fact that we'll accept from field theory or from commutative algebra, that polynomial ring, what you have done to the polynomial ring is what you have done in constructing this polynomial ring is that you started with the field k and you have added n indeterminates, and these n elements are algebraically independent by definition, because any try to understand that if you look at x1 through xn, they are elements of this ring, and this ring sits inside its quotient field, so they are also elements of this quotient field. You can think of each xi as xi by 1 divided by 1, just as you think of an integer as a rational number given by the integer divided by 1, okay, and therefore these xi's are all elements here, okay, and the fact that they are all algebraically independent is the fact that if you write a polynomial in the xi's with coefficients from k, and if it is equated to 0, then all the coefficients have to be 0. That is what it means to say that the xi's are indeterminates. The fact that xi's are indeterminates says that they are transcendental over k, and any polynomial relation amongst them is 0 if and only if all the coefficients are 0, okay. That is, in other words, they are all algebraically independent. So it is very clear that x1 through xn are algebraically independent, and therefore the transcendence degree has to be at least n, and then if you do some field theory you can check that the transcendence degree is exactly n. So by this definition you will get that the dimension of an, the topological dimension of an is the same as the Krull dimension of this ring, and that is equal to n, okay. Now let me come back to this this statement here, and that has got to do with trying to do it to all this dimension count even for an affine variety, okay. So let me do this for any affine variety and use this. So you see, suppose y inside an is an affine variety, suppose y inside an is an affine variety, okay. So y is an irreducible closed subset, okay, and of course y is, well, 0 set of the ideal of y with of course ideal of y a prime ideal in the polynomial ring xn, okay. Now you see so what I want to say is that a statement similar to this also can be made for affine varieties. So what is happening here is the topological dimension of affine space is the Krull dimension of the ring of functions on affine space. See, that is what the first statement says. The topological dimension of affine space with respect to Zariski topology is the Krull dimension of the ring of functions on the affine space, and the Krull dimension of the ring of functions on the affine space is the transcendence degree of its quotient field over the base field, okay, which is essentially this theorem. Okay, a similar statement holds for any irreducible closed subset. So what do you expect the theorem to be? The theorem, the fact will be that if you take the topological dimension of Y, okay, notice that Y is a subset of affine space, and affine space has a Zariski topology, so Y has also the induced topology, and in fact Y is itself a closed subset. So therefore any closed subset, the closed subsets of Y are precisely the closed subsets of affine space which are contained in Y. There is no difference, okay. And so Y if you take the Zariski topology induced on Y and you look at the topological dimension of that will turn out to be equal to the dimension, the Krull dimension of the ring of functions on Y. See, look at this statement. The topological dimension of the space is the Krull dimension of the ring of functions on the space, and the ring of functions on the space is all the polynomials. So here I should write ring of functions on Y, okay. But what is the ring of functions on Y? The ring of functions on Y, to get the ring of functions on Y, you will of course all polynomials which are functions on the whole affine space are also going to be functions on Y, because after all you take a polynomial, I can evaluate it on affine space, I can also evaluate it on a subset of the affine space. So I can take all those polynomials and restrict it to Y. But the point is, two such polynomials, two different polynomials there may still define the same function on Y. That is because their difference may be a function which vanishes on Y. What this tells you is that the functions on Y are the same as the functions here on affine space up to translation by elements of the ideal Iy. In other words, what you are doing is you are looking at cosets of Iy in the polynomial ring, which means you are actually looking at the quotient ring. So the moral of the story is that the ring of functions on Y has to be the ring of functions on the bigger space, which is affine space, modulo the ideal of Y, okay. So this is the Krull dimension of the ring of functions on the affine space, which is the bigger space k x1 etc xn modulo the ideal of Y, okay. Notice that the ideal of Y is prime, okay, and the ideal of Y is prime, and therefore this quotient is an integral domain, okay. And we are in the situation of this theorem. You are having a polynomial ring over a field, you are going modulo a prime ideal, and then the Krull dimension is actually the transcendence degree of the quotient field of the integral domain over the base field. So if you use that theorem, you will get that this is transcendence degree. So this is by definition transcendence degree, yeah. But before I do that, let me use this theorem, okay. Let me use this theorem, alright. So what this theorem will tell you is that it is the Krull dimension of R is the Krull dimension of the bigger ring minus the height of the ideal by which you are going to get R. So this will tell you that this will be just n minus height of the ideal of Y, and of course this will be equal to transcendence degree of the over k of the quotient field of this quotient ring k x1, which is an integral domain. So so the moral of the story is that you can calculate dimensions for you have a formula for dimensions for affine close affine subvarieties of affine space. Okay, so as an example you can look at y equal to say z of x1, okay, or more generally suppose I take the ideal generated by x1 through xr okay, where inside affine space where r is less than or equal to n, okay, then you can see that so then dimension of y as a topological space is by definition going to be n minus height ideal of y, okay, and the fact is that the ideal, see the ideal of y is just ideal of z of x1 etc up to xr, okay, and you know if you take I of z of some ideal you get its radical, which is you know one of the important consequences of the null ansatz. So what you will get here is the radical of x1 through xr, and you can check that it is its own radical. That's because it's prime. Why is it prime? Because if you take the polynomial ring modulo this ideal, you will get the polynomial ring in the other variables. That's a very easy check. And since when you go modulo this, you get a polynomial ring in some variables which is an integral domain, this has to be prime, and since this is prime it's already radical, okay. So you will get this, and therefore and you know if you take height of Iy you will get r, okay, because you are going to look at a maximal chain like this which starts with something smaller and goes up to the ideal, and you know you can see that since the maximal chain of primes will be for example like 0 properly contained in x1, properly contained in x1 comma x2, properly contained in, and so on x1 through xr, okay. So you will see that the height is r, okay, and but I am saying for example because one has to prove it, okay. The fact that you have a chain like this tells you that the height of this ideal is at least r, okay, because height is supposed to be supremum. The fact is that you cannot get a chain of bigger length, that's a fact that needs to be proved, okay. But if you assume that you can if you believe that, then height of Iy is r, and you will get dimension of the topological dimension of y is equal to n minus r, okay. And this is so in other words what you are saying is the topological dimension of the 0 set of x1 through xr is n minus r. Of course you know if I put n equal to r, then x1 through xn will be a maximal ideal that will correspond to the origin. So the 0 set will be a single point and the dimension will become 0, n minus n, a point will have 0 dimension, okay. So this is so what this demonstrates to you is that you get the most natural thing, namely if you go if you take if you cut down by r equations, then your dimension also cuts down by that many equations. Roughly this is what is happening, but then it's technical to check that this the height of this is exactly r, okay. But what I am trying to demonstrate to you is, so of course here I have used this result. I mean this allows you to do dimension calculations for subvarieties of affine space, closed subvarieties of affine space, and here is a standard example. So the when you take z of x1 through xr, you are taking the locus given by the intersection of all the hypersurfaces. When you take 0 set of any xi, you are looking at the equation xi equal to 0, that is called a hypersurface because it is cutting by one equation. And now what you are doing is, now you are successively cutting by r of these equations, and obviously you should expect the dimensions should also go down by r, and that is exactly what this computation says. And the fact is that this is exactly what you would expect, this is exactly what happens, but the commutative algebra that intervenes is locked in these two theorems, is captured by these two theorems, and that involves the definition of transcendence degree, it involves the definition of Krull dimension, and which in turn depends on the dimension of, I mean the definition of height of a prime ideal, okay. So these are the, I mean this is the commutative algebra that comes in. So so the moral of the story is the following. The moral of the story is that if I draw a diagram with so maybe I can do that. If I draw a diagram with if I draw a diagram with the geometric side here and the commutative algebraic side here, if I start with an, okay, then what you go to is k of x1 etc. up to xn, which is the ring of functions on an. So now you see now this dictionary that what I am writing down is not what I is different from what I wrote down earlier. Earlier I was looking at subsets of an, say closed subsets of an here, and I was looking at ideals here, okay, but I am not doing that now. What I am doing is I am defining a relation, a function which to every set gives its set of functions. So this is a of, so this is a symbol, standard symbol. So a of an k is the set of functions on an. If you give me z affine variety, z of p affine variety, affine subvariety, which is a closed subset, irreducible closed subset of an, okay, then, and if you apply this a, you will get a of z of p is just k of x1 through xn mod p. The affine, the ring of functions on an affine variety is just the quotient of ring of functions, the ambient space modulo the prime ideal whose zeros define that particular irreducible closed subset. So this can also be written as a of an by I of z of p, if you want, okay. So you see now you get a picture. The picture is here on this side you have the affine variety an, mind you an itself is an affine variety because it is an irreducible closed subset, okay, and you have its irreducible closed subsets which are proper affine varieties, and there are the corresponding rings of functions. So the moral of the story is that we have this correspondence between space, the geometric spaces on this side and the rings of functions. So in all of algebraic geometry, the point is that everything that is geometric here gets translated into commutative algebra and vice versa. Okay, so here is, so for example, the topological dimension on this side is the Krull dimension on the other side. That's what the theorem says. Okay, so the notion of topological dimension here corresponds to the notion of Krull dimension there. That is a translation. Okay, that's what you must understand. Okay, so I'll stop here.